Good morning, everyone. Welcome to Berkeley. Welcome to the Full Stack Deep Learning Bootcamp. Let's start with a couple of quick intros. I'm Peter Abil. I'm a professor here at Berkeley. I'm also founder and president and chief scientist at Covariant. At Berkeley, I work on research and teaching in AI and robotics. At Covariant, we work on putting AI for robotics into practice. Other organizers?
Hey, my name is Sergey. I work at Turnitin, and I'm there via acquisition of my company Gradescope, which I actually co-founded with Peter and a couple of other grad students here from Berkeley. I work on AI for education broadly, and I'm sure I'll be talking more about that with you individually.
Hey everyone, my name is Josh Tobin. I'm a research scientist at OpenAI and also finishing up my PhD work here at Berkeley with Peter. I work broadly on applications of deep learning to robotics. So for dexterous manipulation, grasping, and problems like that.
Great. Aside from the three of us, in these 2 days, we'll have 4 guest lectures. Today, we'll have Lucas Bewald from formerly Crowdflower, now Figure 8, which was his previous startup. Now he has a new startup, Weights and Biases. We'll also have Raquel Urtasun from Uber Advanced Technology Labs in Toronto, as well as professor at University of Toronto. And tomorrow, we'll have Jeremy Howard from FastAI and Richard Zoker from formerly MetaMind, acquired by Salesforce a few years ago, and chief scientist at Salesforce. We also have a bunch of sponsors, which we want to thank. There are Google Cloud credits we'll be using in the labs, and there are breaks sponsored by Baidu Ventures and Waymo, and there are scholarships sponsored by Turnitin. All right, so why would you bother with this bootcamp or with deep learning? Maybe let's give a very quick motivation, just in case you were thinking of turning around. Imagine you wanted to build a system to recognize what's in an image. And this is the image, and any one of your friends will say, this should be easy. It's just a coffee mug. Everybody can see it. But how do you write a computer program for it? And you would say, well, actually, it's not that easy to write a computer program for this because a computer doesn't have a visual system like we have. It just sees a bunch of numbers. And just looking at the numbers, it's not clear how to write a piece of code that will say if, then, else, and so forth, and ultimately say this is a coffee mug. This is because these pixel intensity numbers are a very poor representation for capturing what's in an image. So we need something else. And until 2012, the state of the art of the something else was a kind of heavily engineered machine learning pipeline, where you would take an image, turn it into what effectively was some kind of variation of a histogram of where the edges are in the image. You might wonder why a histogram of edges, because when you change the lighting, the edges will stay in the same place. And when you change the viewpoint, the edges will only shift a little bit. So a histogram of edges was the best humans could come up with to capture what is the invariant properties of this image, such that once you have this invariant representation, you feed it into something fairly simple called support vector machine, which is the counterpart of linear regression. In linear regression, you fit a line through some points. If the points lie roughly on a line, it can work great. If they don't, it's not going to work great. Support vector machine tries to find a line that separates 2 types of points. If that's possible, that's great. If that's not possible, it's not going to work well. And for images, that was not possible with these representations. But people would kind of try to keep redesigning these representations in the hopes that then when you feed it in, it'll kind of be nicely separated by the support vector machine. Didn't really succeed. Then in 2012, everything changed. Out of Jeff Hinton's lab at the University of Toronto, it was shown that instead of hand designing these representations of images, what you can do is you can actually learn the representation of the images. You can turn an image into a new representation based on which you can classify by just training a massive neural network. So this neural network had 60 million parameters, which means there are 60 million numbers you get to choose. And if you change any one of the numbers, it'll change effectively the computer program that that neural network is running to make its decision. Of course, setting these 60 million parameters by hand is very tedious. So those parameters were set by looking at a massive data set and tried to make sure that the neural network did well on that data set. More concretely, what it would look like is you would have a bunch of images annotated with what's in them. And then what you'd want is when you feed in an image, some massive processing happens and out comes a decision of what might be in the image. Initially, it's not going to be correct when you just put down a network. You have 60 million parameters. You're going to have made the wrong choice. In fact, you're not going to make that choice by hand. You're just going to randomly put in some weights, and it's not going to do the right thing. But then, as you feed in an image, and it does the wrong thing, you can do a backward calculation to change the weights to improve what it says for this image. And if you feed through enough images, it'll start to understand the pattern of what's in images. What it means is that in a neural network, the weights essentially encode a computer program. And instead of programming by hand, by writing lines of code for making a decision of what's in an image, the code lives in the weights. And the code is determined by the data that you feed in. And if you feed in enough data, the weights will take on the right values. Enough data for ImageNet means like more than 1 million images. And you might wonder then, well, how much did it affect the performance? Here is a graph showcasing ImageNet performance, which is a standard competition on image recognition over years. So 2010, 11, 12, and so forth. Lower is better. This is error rate. In 2010, the winner of the competition sent in a computer program that the organizers ran on a secret stash of images that achieved a 30% error rate, which was the best. Then 2011, not much better. This with traditional computer vision pipelines. 2012, everything changed. And it was not just like a one-time leap forward. The trend was not really moving the needle very much with the traditional approaches, but with trained deep neural networks, it was first a big leap forward and then a big acceleration in progress. At the time, actually, a lot of people were still skeptics because they had been working on these complicated pipelines for a very long time and had a hard time believing that it was possible to just train something from data that outperformed it. So they thought, well, this must be a very special purpose, and maybe it only works for image recognition. Other people thought, well, no, this seems very general. In fact, what this is doing, it's able to learn a pattern from inputs to outputs in fairly full generality. And so what does it mean to be more general? Well, instead of maybe learning to classify what's in an image, you could actually train a neural network to generate a full sentence about an image. And the interesting thing here was that Microsoft put out a data set of images and corresponding captions. And within a very short span, 8 different research groups had effectively the same result. There was a group at Stanford, a group at Berkeley, at Toronto, Montreal, Baidu, Facebook, Google, and so forth. And they all show that it's possible to train a neural network from that data set to caption images. And these are automatically generated. So this is not showing the data set. This is showing a new image. And the neural net says, girl in pink dress is jumping in air. So what that showed is that kind of a phase was reached where if the data set exists and you have the right expertise, you can get the neural network to pattern match on that data set. In this case, output is words, which is a very wide classification range because it's about 200,000 words to choose from, and then again, 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 until you complete the sentence. Some people were still pretty skeptical at the time and said, well, maybe it's still a little special purpose and so forth because, is that really image recognition to generate a sentence? Well, if you want to show a neural network can really understand what's in images, truly understand what's there, maybe generating a sentence is not enough. But what if you could have an image, ask an arbitrary question about the image, and the neural net can answer it? At that point, then, there's not much left that you could claim is not covered by this. So sure enough, somebody created a data set with images, corresponding questions, corresponding answers. And here are some examples of the neural net seeing a new image, a new question, what vegetable is on the plate, and then answering it correctly, broccoli. I really like this one here. How many school buses are there? The neural net says 2, which is correct, because in the back here, there's a second bus, It knows that's two buses, not just one big yellow rectangle for one bus. It also has seen some applications in domains where traditionally humans require a lot of training. So these are things maybe a 3-year-old or a 5-year-old could do. But actually, in medicine, people train for a very long time. For example, to recognize whether a mole might be potentially cancerous or not. But that was shown to be possible with a neural net at the same level. Same for radiology. We can take long training to recognize in X-rays what might or might not be there. But what we saw happen is that neural networks, given enough examples, could be trained to make those decisions also. And in fact, as of April 2018, there is a FDA-approved neural net. What does that mean? It means that the FDA approved this neural net to make medical decisions. What kind of medical decision? Let's say you're a diabetes patient. Then what needs to happen is, as you do your checkups, one part of the checkups is that the doctor should look in your retina to look at the progression of your disease in your eye. And normally the doctor would look at that, and then based on what they see, they would decide whether or not to refer you to a specialist. The decision whether or not to refer you to a specialist can now be made, or since about a year ago, can be made by a neural network that can be fed the image and can say, you should go to a specialist, or you don't need to go to a specialist. Of course, if you can see, big application is self-driving cars. Many, many companies pursuing that. Huge market. Hundreds of companies going after it. The game hasn't really been played out fully yet. I guess it's up in the air who's going to get there first and how many companies are going to meaningfully, I guess, grab some market share there. It's not just for computer vision, though. The notion that you can learn to recognize how to go from an input to a corresponding output is just as applicable as speech recognition. Input is a sequence of numbers corresponding to the pressure in the air, and the output would be a sequence of characters or a sequence of words. Machine translation, same thing. Input would be a sequence of words in one language or a sequence of symbols in one language. Output, sequence of symbols in another language. Now, you might wonder, how long has this been around historically? You might maybe have seen stories about Rosenblatt building neural networks back in the 50s. So why did it become so cool in 2012 all of a sudden? If people were doing it in the 50s, then the algorithm everybody uses called backpropagation, invented in the 80s. The architecture, for example, for computer vision, most people use some variations thereof, but not that different. Convolutional networks, also invented in the 80s. Why is this happening since 2012 and not before? Well, 3 factors. One is data. These neural networks, to train them well, require a lot of data. And this ties back into a very fundamental theoretical property of these networks, is that they're universal function approximators. They can approximate any function when they're big, but that also means that you need a lot of data to narrow down what function they should be approximating. And so a lot of data is needed. And until 2012, the reason other approaches performed better is that these other approaches essentially were able to incorporate a lot of human expertise, combined that with a small amount of data, and a lot of human expertise combined with a small amount of data was outperforming a small amount of data fed into a neural network. Compute to process that data takes a long time. The breakthrough that happened in 2012, training that neural network to have the ImageNet breakthrough took 6 days on state-of-the-art GPUs at the time. You can also imagine that you don't just train this once and you're done. You need to train with different hyperparameter settings, iterate maybe over the architecture and so forth. So it's not just a one-time 6-day run. It takes a while if it takes 6 days to do one experiment to get to the good results. And also some new ideas, of course. But a lot of these new ideas, I would argue, are enabled by having the data and the compute that allow you to investigate those ideas. Often, if you need, let's say, imagine Rosenblatt trying to investigate, I don't know, ResNet instead of regular ConvNet. He would have to wait like years before he can see any result with the computers of the 50s. So he couldn't really meaningfully work on that. He chose other problems to work on. So data we're only going to get more of. So that suggests that neural nets will only become more powerful, more capable in the future, assuming we can process the data. compute in AI experiments keeps going up. So this here is measured in petaflop days. A petaflop is roughly, extremely approximately the amount of compute we have in the human brain. And so a petaflop day would be roughly how much compute we can do in one day as a human. So 1 here means 1 petaflop day. 0.1 is 1/10 of a petaflop day, and so forth. AlexNet training used about 1% of a petaflop day. Then AlphaGo 0 used about 3,000 petaflop days. So in just about 5 years, the amount of compute used to train one of the most prominent neural networks of the day went up by a factor of 300,000. And the trend seems to be continuing to go upwards. So it seems like we get more data and manage to put more compute to use on these experiments. So likely neural nets will continue to kind of do more and more capable things in the foreseeable future. So neural nets will be powerful. So why should you take this class, and where does it fit in? If we look at other classes, a lot of great classes out there. There's DeepLearning.ai by Andrew Ng, who was my PhD advisor. The Deep Learning book by Ian Goodfellow, Yoshua Benjo, and Aaron Curvell. Then there is FastAI. There is Keras-based tutorials. So there's a lot of other things out there. Where we position this course is here. And what does that mean? These focus mostly on the math, the foundations. And we kind of assume that you already have a lot of those by the time that you're here. Then these ones focus a lot on the practical training, on running some new experiment. Let's say I want to run something on this data set and see if I can get it to work. But then here we'll focus on how to ship projects. So not just what's maybe some new architecture idea, but also how do you deploy things? How do you make sure they're easily testable, maintainable? You can improve upon them when you get new data, and so forth. So more what you need to put it into practice after you already have the foundations. Another reason to look at this class, aside from the content, is that it's good to bring people together who are working on similar things. Often when you're working on something alone, it's much harder to make progress. You might get stuck on something for a very long time. So we try to provide a lot of time for breaks also in these 2 days, such that you can talk with each other and hopefully build some connections for the future. And hopefully, if you don't have your dream job just yet, hopefully this can help you get there very soon. How we develop the content? By having a lot of conversations with engineers at a lot of the leading companies applying deep learning in their production systems. And so we try to bring together what we learned from those conversations into what they said, well, this is really critical. This is what I would want to see in somebody we hire that they would be capable of doing, and so forth. OK, schedule for these 2 days. We just did the intro. Then we'll start with setting up machine learning projects, our first break. Then we'll do our first labs, where you'll get to actually already code 3 things up yourself, 3 labs. We'll have lunch together, infrastructure and tooling, 2 more labs, another break, data management, hiring and jobs. And then we'll have our 2 guest lectures for today, which are Lucas and Raquel. Happy hour tonight. And then tomorrow we'll start with training and debugging, another break, 2 more labs, lunch, testing and deployment, another lab, another break. Then we'll look at something that's a little separate from everything else, which is what are some of the current frontiers in research. And so where might you expect that some of the new breakthroughs will be coming from in the near future? We'll have 2 more guest lectures with Richard Soker and Jeremy Howard, and then happy hour to wrap it all up. Any questions? Yes?
So in the ImageNet, it was found that if we add a little bit noise, then all of these networks are going to perform poorly, then what's the solution that we can address here?
Yeah,
To
so
justify that they're doing good. Because if you add a little bit noise on dog, then you're going to detect it as fish.
yeah, so the question is about adversarial examples. So, and since the question is, I told you neural nets are doing very well, and you're saying, well, there's some evidence that in some cases neural nets don't do so well, so what to believe now? So one thing is that if you add random noise to an image, it's very unlikely that'll lead to the neural network making the wrong decision. So what happens in these adversarial examples is that you have a neural network, and then you set up an optimization problem where you say, given that this is the decision-making process, what is the smallest change I can make to the image such that it'll make the wrong decision? And it turns out, because it's such a high-dimensional space, and you're learning such a high-dimensional space, that typically you end up with some direction in which you can make a small change such that it makes the wrong decision. There's different ways to think about this. One way to think about it is that, well, you just don't have enough data. And then what you can do is to say, well, how can we augment our data set to make this more robust? And a lot of the defenses against adversarial examples effectively do that. They will say, OK, we should just randomly perturb our images and say that anything within a small sphere in this high-dimensional space around an original data point should be classified the same. But to cover that sphere is, of course, like enormous amount of data to cover a high-dimensional sphere. So then instead, people actually just run the adversarial example process. They'll say, oh, what's the adversarial example for this image? OK, let's feed that in as another labeled example, because we know I only moved epsilon away. And that's one way to kind of robustify a training. Other tricks, there's definitely still things like that where people are still making progress on making neural networks more capable, more robust. But I would say it's not the case that just a random small change would result in a mistake. It's more like if you carefully look for the exact right small change, then you can fool it. But there are techniques that explicitly try to address that. Not that it's fully solved, that's for sure, but there is good progress in that direction. Yes?
Chargers or outlets?
There should be outlets on the floor in various places. Maybe not everywhere. Yes?
You said that the data has gone up 300K, right?
Mm-hmm.
What about the size of the network? Like, are they getting wider? Are they getting deeper? Or are they plateauing?
OK, so the question is, the compute went up by a factor 300,000. This graph over here. So how about the networks themselves? The networks have grown quite a bit, too. I don't have a graph on this, and I think Sergey will probably have a graph on this later when presenting some computer vision examples, where the size of networks has gone up. Interestingly, people have managed to make the networks bigger and bigger and bigger, while not necessarily making the number of parameters larger. And the number of parameters tends to determine how many data points you need. And sometimes you cleverly architect things. You can reduce the number of parameters even though the network has become bigger. For example, the recent transformer architectures have a lot of parameter reuse that even though the network is becoming really big, the number of parameters hasn't grown all that much compared to the size of the network itself. Yes?
Getting back to the very first question, is there an automatic way to generate those adversarial examples based on the base or the data so that we can automatically augment and make it
yeah, so the question is about adversarial examples, and is it possible to generate them automatically? Oh, yeah, it's very easy to generate them automatically. So all you do is you take an image, and then, at least for image recognition, it's very easy. You take an image, and you run the forward pass in the network. You look at the classification. And then you say, well, maybe I want something else. Maybe it was correct, because it was well trained for regular images. You say, oh, well, it classified as an elephant, but I want it to be a penguin. Then you look at the penguin output, and you say, OK, how can I maximize this output? And instead of backpropagating, normally backpropagation would say, it's an elephant, supposed to be an elephant, let's reinforce that. You would say, I want to now backpropagate to make it a penguin. But instead of backpropagating into the weights, that's the network, you don't get the modified network, you backpropagate all the way back into the pixels, which is the exact same kind of calculation as backpropagating into the weights. is just like after you pass the entire network and you're done with weights, you hit the pixels and you update the pixels and in the direction that makes it more likely a penguin, and that'll get you what you're looking for in terms of adversarial perturbation.
Do people do that? I mean,
Absolutely. I mean, that's how people tend to generate adversarial examples. If you look at the, I want to make sure we transition to the next lecture. So let's take the remainder questions maybe in break, or maybe there'll be good context. Do you have a logistical question?
Yeah.
Logistical, okay.
I read about an optional certificate. I was wondering if you could speak about that really quickly.
Okay, optional certificate. Sergey, do you want to comment on that?
I was just wondering if you could speak a little bit more about it, maybe what exactly is going to be on it, or when because I saw in the itinerary, I didn't see like when the project.
No, the optional certificate.
Oh, I'll talk about that this evening.
Okay. Yeah.
Okay. One quick logistical thing, make sure you're on our Slack such that you can communicate with everyone else here and with us. All right, thank you.